Hello, everybody. So, after the discussion we had in the previous video, and I hope we are now very familiar with using the chart or Colebrook equation to calculate the friction factor. And before we proceed, I just want to just show this slide, and I think it's an important slide because sometimes when you go through a lot of details, we miss the main point of what we're doing or the main goal of this whole discussion. So I just want to quickly revise where we are now after all these discussions. What is the point that we are or what we achieved and what we can do next. So we're still dealing with the conservation of energy equation, which is modified Bernoulli equation or the general energy equation, which we use to calculate whatever the parameter that we're interested in, the pump head, the pressure, velocity, height, or whatever. This is what we used to do in chapter 5, but here in this chapter we were focusing on this term, which is the head losses. And instead of having it as a given information, as we used to do in chapter 5, we are now able to calculate these losses. And the way we calculate it is using Darcy's equation, and we discussed this a lot on why we use Darcy equation, and this is how Darcy equation looks like. And what makes this equation very interesting, we like to use this equation, is that we can use it for almost all the cases that we have. So it's not like Poiseuille equation that is only valid for laminar flow. This equation is valid for both laminar and turbulent flows. And what makes it valid for both is this friction factor. And this friction factor can be calculated with different ways based on the type of flow we have. So for laminar flow, it's only function of Reynolds number, and we know it's 64 over Reynolds number for circular pipes, and there were other relations for different pipe sections. For turbulent flow, we have the relation that we discussed in the previous video, which is the friction factor is function of Reynolds number and the relative roughness, and we can calculate it using Colebrook equation or the Moody diagram. So this is what we are or we achieved till now. So back to the big picture, we now can calculate the losses based on the parameters we have or know about the system, the fluid properties, the dimensions of the pipe, the flow rate, or the velocity, or whatever. Okay, so this is a very good point that we reached now. So the what we're going to do now, or for the rest of this part of the chapter, is to see usually what kind of information we try to calculate in these kind of systems. So we have three types of cases that we usually deal with. The first is that we want to calculate the losses or the pressure drop during the fluid flow, and we know the pipe dimensions, the length, diameter, and the velocity or volumetric flow rate or the mass flow rate, because the three are very related to each other. So in this case, this is a very nice case to deal with because we know all the information that we need to calculate Reynolds number. We know the density, the viscosity of fluid. Of course, we must know them. We know of course we know the roughness of the surface from the pipe material. So we know the Reynolds number, the relative roughness, and we can calculate the friction factor directly, substitute in Darcy's equation directly, and calculate the losses, and then substitute in Bernoulli equation to calculate the pressure drop if we are interested in the pressure drop. So in this case, it's a case that we can solve directly without, in straight steps, and the next until we reach the final step. For type 2, we have different givens and different requirements. Here we know the losses or delta P, and we are trying to find the rate, the flow rate, whether it's the volumetric flow rate, mass flow rate, or velocity. As we said, if you know the volumetric flow rate and the diameter, you know the velocity. If you know the mass flow rate and the density and the diameter, you know the volumetric flow rate and the velocity. So we know, you know everything, or the three of them. If we know only one, we can know the rest of them. The third case is a different case where we want to calculate the diameter and we know the length, the pressure drop or the losses. We know the rate, the flow rate, mass flow rate, volumetric flow rate, or velocity. And here in these two cases we will face an issue, and this issue is that we cannot calculate the friction factor directly. Keep in mind that for calculating the friction factor, we need to know two information: the relative roughness and Reynolds number. Reynolds number is function of velocity, so we cannot calculate the friction factor without the knowledge of velocity. So this makes the solution kind of tricky in this case. Here it's even more trickier because we don't know the diameter, and Reynolds number is function of the diameter. Relative roughness is also function of the diameter. So this makes it even more that's not much more difficult, but it's one more level of complexity, which is not a big deal if you compare these two cases. So for these cases, we solve them by what we call iterative solution, or by trial and error, meaning that we assume a value and then we recalculate it until we reach the right value. So what we are going to do is, in this video, we are going to discuss the first case, solve two problems related to the first case, and for the type 2 and type 3 would be for the next video, inshallah. So for the the first case, or the first example we will solve is about a pipeline that is transporting crude oil in an 8-inch galvanized pipe, iron pipeline. So we know the pipe material, we know the diameter of the pipe, and we know the length of the pipe. It's 1000 meter, which is 1 kilometer. And we know the specific gravity and the viscosity of the oil. So we know the density and the viscosity. And we want to find the losses. So it's a typical case one. Okay. And we know the volumetric flow rate. So for this solution, if we want to calculate the losses, so we'll directly substitute in Darcy's equation. So it's simply, we will first we will calculate the velocity by calculating the volumetric flow rate over the area, which is going to be 3 meters per second, and then we will calculate Reynolds number, which is rho ud over mu. We know the density, we know the viscosity, we know the diameter, we know the length, of course, the velocity. Of course, making sure that the units are homogeneous is needless to say. So this is something that you have to make sure you take care of very, very well from the beginning. And this is something I really encourage you to do, is that this is what I put here, is to do all the unit conversions and all the check on the units before you start the solution. It's something that can be easily missed, so it's better to take care of this very early and make sure you are done with it from the very beginning. Now we know Reynolds number. We want to calculate the relative roughness, so we need to calculate the surface roughness. This is galvanized iron pipeline. So if we go to the table, it says here galvanized iron, it has roughness of 0.15 millimeters. So if we go back to here, so we know the 0.15 millimeter, we'll convert this into meter by dividing by 1000, and from this we calculate epsilon over d, and from this we know the value of epsilon over d. So this is good news. We know the relative roughness, we know the Reynolds number. Of course, this Reynolds number is more than 4000, so it's one thing you need to pay attention to, that this is a turbulent flow, so you cannot apply the 64 over Reynolds number for friction factor because it's a turbulent flow. So let's check. If we try to calculate the friction factor using this Reynolds number and this relative roughness, so it's around 7100 or 7.1 times 10 power 3 Reynolds number, and 0.0007 for epsilon over d. So if we go back, this is 7 times 10 power 3, so it's going to be here, this line, okay, this line here, and for epsilon over d it's 0.007, so it's between these two lines. So if we go between them until here, it will be something around here I think. You need to be careful with this because it's very easy to go up and down. And of course, if you are doing this with a piece of paper, it will be much easier because you can use the ruler or something to track the lines in a better way than just doing this visually with your eyes. So it's I'm just trying to make sure that I am in the right spot. It's very hard to do that, but anyway, so it's I think if I'm doing this right, it's going to be around here. It's 0.041, I think so. So let's check. So oh, it's very far. It's 0.0347. Maybe I put the wrong number. Oh, it's 0.0007. Oh, this is the mistake. Yeah, you need to pay attention to this. You don't do the same mistake I made. It's 3 zeros before the 7, and this is why I was looking somewhere else. So it's going to be this between these two lines. So if you go here, it's going to be somewhere around, and you see the lines are getting very close to each other. So it's going to be somewhere here. I think it's going to be somewhere here. So I would say it's going to be 0.035. It should be this point here. So it's 0.035, and what we got here is 0.0348. So it's the same thing. Okay. So this is the friction factor, and now we'll just substitute directly in the equation. We know everything, so it's going to be L over du square over 2g, and this is 78.54 meters. If you want to calculate the head losses, what the textbook does is just multiplies rho g times HL, and it's actually from Bernoulli equation. If you think of this as a horizontal pipeline with the same diameter, so it's the same velocity on the two sides, the same height, so they will cancel out from both sides. There is no turbine, there is no pump, so it's going to be only delta P over rho G equals HL. So that's why delta P equals rho G HL. So this is the pressure drop due to the head losses. So this is the first problem. The second problem is a similar problem, but it's about a fire hose, and the code requires the pressure at the outlet of the pipe to be 65 psi, so that the water can go further distances. And the pipe length is 250 feet, and the diameter of the pipe is 4 meters. We know the volumetric flow rate is 1.5 foot cube per second, and we want to find the minimum pressure allowed at the pumper truck. So there is a pump in the truck, and it pushes water out. So after the pump, so pump is not going to be part of the Bernoulli equation. After the pump, what is the needed pressure so that the outer pressure is 65 psi as required by the code, and we know the roughness is 0.03 inches. So it's very similar to the previous problem. Even we know the roughness as a given information in the problem statement. We don't need to find it from the table. But the only trick here is the units. That this is in US units, and US units are kind of tricky in this kind of thing. So let's go step by step. So first we will apply. These are the information that we have. Of course, it's water, so we know the density. The viscosity is 10 power minus 3 kilogram per meter second. So we will convert this into pound mass per foot second, and then the area is pi over 4 d squared. So this is the area. We know the velocity is the volumetric flow rate over area. So it's almost the same procedure that we followed before. And now we apply Bernoulli equation. Also, we have the same height. We assume because it's the minimum pressure, so it's assumes that this is the same height. So it's the same height, the same velocity, because it's the same pipe, and there's no pump, there's no turbine. So it's also going to be delta P over, but in this case, yeah, it's the same thing. Delta P over rho G is HL, but here we know P2. So P1 is can be calculated, not just the losses. So for the losses, we will calculate also Reynolds number and the relative roughness. So Reynolds number is 532 thousandths and relative roughness 0.0075. Let's go back. It's 5.3 times 10 power 5. So this is 4 times 10 power 5, 5 times 10 power 5. So it's going to be between these two ticks. Okay, so it's going to be somewhere here. So if we go up, it's going to be somewhere here, and it's 0.007. So now it's 0.007. So Let's make sure we are in the right place. 0.006, 0.007, so it should be here, and this point here. So this is I missed it. So if you go to the right, it is 0.034. I think it will be something like this. So from Kolbrek equation, it's 0.0346. So we are getting very, very close. So it's 0.0346. And now we can calculate the losses. And of course, the losses, the head loss is going to be in feet. So this is units of length. Now it's going to be the same thing. We will just substitute in this Bernoulli equation to get the pressure. But it's going to be a little tricky here because the pressure has units of PSI. PSI is pound force per square inch. And we want to divide this pressure by density and G. So density and G have units of of pound mass, foot, and second. This is pound force per square inch. So we have to unify the units, which needs one more step here. So pressure has to be in units of pound mass per foot second square instead of PSI, or pound force per inch square. So we can convert pound force into pound mass foot per second square, because we know 1 pound force is 32.2 pound mass foot per second square, and we know the inch is 1 foot is 12 inch, so we multiply it by 144 over 1. So now the numerator is going to be pound mass per foot second square, okay, and this is going to be pound mass per foot square second square. So the result is going to be in foot. So this is foot and this is foot, so the units are homogeneous, and we can calculate the pressure, which will be whatever you can calculate the value. This is pound mass, this is not F, this is M. This is pound mass per foot second square, and then we will divide by 32.2 144 to return it back to PSI. So it's 116.6 PSIs. So this is these are two examples. The main trick in the second problem is the units. I cannot see anything different from the first problem. Anyway, so now we got to solve two problems on the first type of problems, which I think is a very, very straightforward case. Inshallah, next video we will go through the next two types, and we'll see how to deal with them. So I'll see you then, inshallah.